Welcome back. Now let us manipulate the energy functions and see what we get. First, we will work with the thermal energy U and the enthalpy H. Notice that the definition of H contains only U and PV, does not contain the entropy. Because entropy is not involved, when we work with du or dH, we do not expect to encounter the second law of thermodynamics. Let us see what happens. First, let us look at thermal energy U. The first law tells us, and let us now separate dW into the expansion component, PdV, and other components. So, we will be able to write this as du plus PdV plus dW other. This term and this term is an expansion of dW. Okay. Now, what does it mean? The one simple conclusion we can come to is the following, that if V is constant, that means constant volume process, then we will have dQ at constant volume will be equal to du plus dW other. Nothing really great. Now let us look at enthalpy. We have H equal to U plus PV. Let us expand it. Differential of H dH is du plus PdV plus VdP. Now notice that we have from the earlier expression du plus PdV is dQ minus dW other. So let us replace it like that, and you will get this equal to dQ minus dW other plus VdP. Now let us transpose dQ to one side and consider a process in which pressure is constant. First we write dQ equals dH minus VdP plus dW other. And now consider a situation where P is constant. So this term drops out, and then you will get dQ at constant pressure equals dH plus dW other. A relation similar to the relation which we got earlier. This is the relation at constant volume, this is the relation at constant pressure. Now let us go over to the Helmholtz function and then Gibbs function. These two energy functions contain entropy in their definition, and hence we will need to use the second law. We will also perhaps use the property relation which relates ds with du and dV. Let us first look at the Helmholtz function. We have the definition of A, which is u minus Ts. Expanding this, we will get dA equal to du minus Tds minus S dt. Now replace du by the first law. So this equals dQ minus dW minus Tds minus SDT. Transposing terms on the left hand side, we will get dA plus dW plus SdT, this will equal dQ minus TdS. But we know from the second law of thermodynamics that dQ minus TdS should be less than or at most equal to 0, and that means the left hand side of this is less than or equal to 0. And now consider a process in which T is constant, an isothermal process. In such a process you will get dAT plus dWT, T constant, so dt will be 0, should be less than or equal to 0, or dWT is less than or equal to minus dAT. Now that means, what have we concluded? That if we maintain the temperature constant, that is a isothermal process, then the maximum work that can be obtained is the reduction in the Helmholtz function. So the Helmholtz function represents something like an energy potential. See, remember, in the general idea of a potential in physics is you reduce the potential and you extract something out. Okay. So here we notice that the Helmholtz function can be considered as a energy potential, the reduction in which represents the maximum possible work which can be executed by our system in an isothermal process. And because of this, earlier and even now quite often, the Helmholtz function is also known as the Helmholtz potential. Now let us move to the Gibbs function. The definition of the Gibbs function is U plus PV minus Ts, which is also H minus T. Okay, let us look at the first direct definition. Expand it, you will get dG equal to du plus PdV plus Vdp minus Tds minus SdT. Now let us expand du using the first law, that will be dQ minus dW plus PdV plus Vdp minus Tds minus SdT. Now you will notice that here we have a combination dW minus PdV, that will be dW other. So these two terms minus dW plus PdV will become minus dW other. And now when we transpose terms, you will get dG plus dW other minus Vdp minus plus SdT equal to dQ minus Tds, which from the second law of thermodynamics is less than or equal to 0. And that means if you put dW other on one side, you will get dW other is less than or equal to minus Tg plus Vdp minus SdT. Now consider a process which is at constant pressure and constant temperature. A very simple situation where this occurs is change of phase. And if you consider more complex systems, chemically reacting systems, then such processes occur quite often in chemical reactions and electrochemical reactions. So under constraints of constant pressure and constant temperature, we end up with dW other under conditions of constant pressure and constant temperature will be less than or equal to minus dG under the same conditions, constant pressure and constant temperature. So, this tells us that in a fashion similar to that of the Helmholtz function, the Gibbs function also represents a sort of potential, the decrease in which represents the maximum work other than expansion work which can be obtained in a constant pressure, constant temperature situation. The Gibbs function is very useful during change of phase and during chemical reactions. We will consider some situations of change of phase, but in this course we will not be considering situations where chemical reactions take place. Thank you.